Presentation, I want to say a few things about intelligence that is produced in cooperation of many small agents, where we define small as agents that we ordinarily wouldn't consider very intelligent. They might be able to process information, but they certainly on their own wouldn't be able to solve the sort of problems that they can solve collaboratively. And I thought it'd be fun to start up with a game of life, or cellular automata. So you probably have seen this sort of stuff. This is an animation that actually works. We have these, this is called the slider gun. So the game of life was developed by Conway. And the agents have very, very simple rules, or the maybe not the agents, but cells on the grid either die or they continue to live, or they spawn a new entity. Just some very, very simple rules. Have a look at it when you get a chance. I think this article over here takes a little bit of time to load. Has an animation in it that that lets you play with it. No, sorry about that. So again, this is the original article in which was proposed. It was introduced by Martin Gardner in Scientific American. What I really want to have a look at is swarm intelligence, and so let's do that. I had a brief session in one of the sections the other day, but I thought I wanted to have a more in-depth coverage of swarm intelligence. So swarm intelligence is where we have many, many agents. We typically look at ants. We also look at flocks, and we look at bees. And the collective behavior enables them to solve quite complex problems. What we're going to be looking at is as path finding problems, which are optimization algorithms typically. Think about the traveling salesperson problem. So that's a hard problem to solve. Again, this is an optimization algorithm, so it's not guaranteed to find an optimal solution, but it's guaranteed to find, not guaranteed, but it typically finds a very, very good solution. So we had to look at genetic algorithms. And so today we're going to look at ant colony optimization. So what's interesting about ants, the way they work so well is because of pheromones. And so if you look at some of the biology of ants, they actually have quite a number of pheromones. Some of them are used to indicate danger. The one that we're going to be looking at is for foraging, so food finding. So let's have a look at that. So the idea is that we use ants, in this particular example, to do optimization. But I thought it might be best to sort of like show you first an animation. And so it's this one over here. You kind of have to download the code. And of course, that's always risky. And so let's see what we can do. So let me ants misspelled. No, it works. So what we have over here is an anthill and a food source. And so the ants randomly go out. That very much is what biologists tell us. And then when they find this food source over here, they come back and they lay a pheromone trail. And so then what other ants will do is they will follow the pheromone trail to go to the food source. And eventually this one here becomes hollow, and then that has been exhausted. So let's see what we can do. And we also know that ants eventually come back. So after a while of foraging, they come back to the anthill. So over here, we have now see that some ants are sort of like laying a pheromone trail. So now the ants are all coming back. And so new ants are coming out. And so again, we model that with a probability distribution that they actually follow the ant trail. And again, many of them do not, because it's still a very, very weak trail. But as the food source, as more and more ants discover the food source and go back, eventually a pheromone trail will build up. And so as you can tell, red ants are sort of like following this pheromone trail quite a bit. And so eventually it gets to be depleted. So that's the idea that ants lay this pheromone trail that helps other ants and themselves later on to find the food source. Now, pheromones are chemicals, they decay, and so eventually, as this one gets to be empty, no more ants will lay pheromones, and so we will then see that this pheromone trail completely evaporates. And so then, presumably, they go to, well, we know that they're going to look for different food sources. All right. Okay, so just about out. And so now the pheromones will decay. And what that means is that ants will just simply look at different food sources. All right, well, let's stop this thing and do another one. So the idea over here is, we have two food sources. Let me just get going with this thing. And we kind of want to find the strongest one, right? Or at least we want to find that there are two food sources. And so eventually ants will go, yeah, so ants do lay pheromone proportional to the quality of the food source. We kind of know that too. But again, it's better to go to two food sources rather than one. As you can tell, this is pretty good. And so this one builds up stronger because the food source is stronger. And so ants also tend to go down this one over here. Okay, let's stop this thing. Then you get the idea. And so this one over here is where researchers will try to understand this thing a little bit about why does this all work. So we have an anthill over here, we have a food source over here, and so they rigged it that there's a path from here to here that is kind of short and the path from here to here that is longer, I think twice as long. So what will happen is we don't see the ants going out until they come back. Yeah, there we go. So you hopefully see a little bit. And so ants find some food, and then they either have to go this way or that way. Some ants go this way, some ants go that way, some ants go that way. And so eventually, as you might guess, this pheromone trail will build up much, much stronger than this one over here. And the reason that is so is because ants that take the short way home, so to speak, are obviously much, much faster than ants that take the long way home. And so that's what will happen is that ants that go out then will follow this pheromone trail to the food source, so they will find the shortest path to the food source. So with my luck, this is not going to work out in this animation here, but as you might imagine, that's what ought to happen, and that's what typically does happen. So again, the idea is that ants lay pheromones on the way back to the anthill, and since this is so much faster and this one takes so much longer, about twice as ants arrive much, much faster at home than on the other one. The idea, though, is that these things are designed to find the shortest path to a food source. So that's kind of the idea. All right, well, let's all have a look at how one might go implementing an ant system in the context of the traveling salesperson problem, which we know is very hard. So let's stop this one over here and move away from it. Let me terminate this. Sorry about that. So here are some slides from the book Swarm Intelligence from Natural to Artificial Systems. This is section 2.3. The book was written by Bonobo, Dorigo, and Thoreau. It was written quite a while ago by now. Some of them eventually went into consulting to make some money off the research that they did. So there are some of the algorithms that I'm going to present are from that book. There are a few other images that I grabbed from MapQuest and that I made myself. But most of the images are from that book. So what's the goal of TSP, the traveling salesperson problem? The goal is to find a closed tour of minimal length connecting n given cities. And so it's typically represented as a graph problem. Each city is a node, and the paths between them are edges. So the reason these people, three people, Dorigo, Colorni, and Manizzo, chose TSP is because it's a difficult problem. It has been studied a lot. There are many test sets available and many other algorithms that you can run comparisons against. And again, we have seen a moment ago that ants appear to be good at finding shortest paths. So let's see how good they really are. I'm going to be showing you two systems. First, a basic system and then an improved system. So the idea is ants build a solution to TSP by moving on the problem graph from one city to another until they complete a tour. Doing an iteration of the AS algorithm, each ant builds a tour executing one step for each node. For each ant, transitions from one city to the other depend on a couple of things. Has the city been visited? Obviously, we don't want to produce cycles. And then the heuristic desirability, where they call this the visibility of connected cities, pretty much the distance, the inverse of the distance, as well as the amount of pheromone trail. So again, if the city has been visited, it's out. But if we have choices, we're going to look at how far away is the city. Again, we take the inverse. And then what's the strength of the pheromone trail to the edge. And so, here's a pretty picture of Western Europe. And so, it's a graph. We want to find a tour, of all the major cities, London, Paris, Berlin, Munich, Milan, Madrid, and Barcelona, Rome, those sorts of places. So let's see how we can do that. So here is the pseudocode. So what we're going to do for every edge, we lay a very, very small random amount of pheromones. So we're going to explain what this is later on. So then we have an ant, we have m ants, and we randomly place them on a city, okay? Or we place them on a random city, I apologize. So T plus is the shortest tour found so far, and L plus it's its length. And so this is something that's a global variable that we're going to be updating. So it always represents the shortest tour so far. We might run this thing for a certain number of iterations, or we can certainly terminate once the tours don't get any better. So here are the ants. And so for each ant, we build a tour by doing this n-1 times because they're ant cities. So we choose the next city with the following probability. And I will explain this formula here in a moment. So I is the current city. So let's have a look at this thing. Well, I is the current city, J are the neighboring cities, T is the tour, K is the ant. So on tour T, we have perhaps different pheromone trails. The visibility shouldn't change. And so that's kind of like the idea. So what we're going to do is we're going to look at the pheromone strength between I and J, city I and J. Again, J are the cities, the neighboring cities, on tour T. Again, the visibility doesn't change. These alpha and beta tuning parameters, I apologize, that help us, sort of like bias it towards visibility or the pheromone strength. And what we do over here is we just sort of look at the sum of all of these values here to normalize it. So we just simply normalize this thing. So that's the transition rule. Again, what I just mentioned to you is explained over here. J is the city still to be visited. Obviously, we don't look at the ones that we already visited. Okay. The visibility is 1 over the distance. And then we have the pheromone strength. So that's it. So we're going to run this algorithm a little bit. At the end of the tour, each ant lays pheromones on the edge. On each edge it has used. And again, the amount of pheromones is proportional to the performance of the ant. The other thing is that the pheromone intensity will decay over time. So this is where we simulate some of the stuff that we have seen. Let's have a look at the algorithm. So now what we're going to do is we're going to compute the length of a tour produced by ant K. We'll simply check, did we find an improved tour? If so, we update T plus and L plus. Otherwise, we're going to lay pheromones on each edge ij as follows. So notice that this for loop is only going to be run once over each edge. And so we're going to update the pheromones for each edge just once. However, we will consider all the ants. So how are we going to update this thing? So again, edge I to j for tour t. This is a tuning parameter over here. We'll see some values in a moment. And so this is the decay, right? So if it's 0.8 or 0.9, then for 0.1, that's how much we're going to decay. So probably want to keep it. So this one here is probably, it's typically going to about 0.1, 0.2. So we're going to keep most of it. This one here I explain in a minute. So let's have a look at this one over here. So this is the delta that we're going to add between edge I and j. And we're going to calculate it over here. So now the ands come in. So k, 1 to m, those are the ands. And so we're going to look at the pheromone strength that we should add based on each and's tour. And as I mentioned a moment ago, it depends a little bit on the quality or the length of the tour. And that's the formula that we're going to use over here. So we're going to look at and k. We're going to look at its solution, q, and we divide it by, I'll tell you what q is in a minute. We divide it by the actual length that it has found. Okay, so what is q? So this is kind of interesting. Q is kind of a tuning parameter. The value is in the vicinity of the expected length of an optimal solution. So typically we use a different algorithm, the quick algorithm, to find a reasonable ballpark tour. And so we could use the nearest neighbor heuristic, which is a greedy algorithm, to find a value. So what is sort of like a ballpark figure, something that is not great, but not horrible either. And so we divide the tour found by the and, we divide q by the length of the tour. Okay, and so obviously the shorter it is, the higher this value is. If the ant didn't go down that pheromone, that edge, then it is 0. Okay, so and again we do that for each ant, and so now we know the delta that we need to add to this edge. So there you have it. We updated the pheromones. Now again, let me explain E here, which stands for elitist ant. So similar to genetic algorithms, where some of the variations keep an optimal solution in the populations, they either automatically get to the next population or they get to mate with some of the other entities of the population. We do the same thing over here. So elitist ants are added at every iteration to reinforce the best path. So that's the idea. So they reinforce the edges belonging to the best tour found. Now notice the best tour we know is T+. So we're simply going to run 1, sometimes 5 ants down this tour. So we calculate the regular pheromones, for all the ants, and then we say, okay, let's reinforce the best tour a little bit. That's what we're going to be doing over here. And so that's it. And so notice that this is the best tour found so far. Might not have been on this iteration, but on any of the prior iterations. So we simply reinforce it, give it a little bit of a boost. So then what we do is once we lay the pheromones, we update them, we add them to the next generation, and then when we're done, we print the shortest tour. Here are some tuning parameters. So the decay rate 0.5, m is equal to n, I think q was the number of cities. This is the initial value that the initial pheromone value that we put, very, very low. Elitist ants, 5 elitist ants, as I mentioned to me. Tuning parameters, alpha, beta. So let's briefly go back to that one. That has to do with this one over here. So we do favor heuristic distance over the pheromone strength in this particular algorithm. So they validated the algorithm, and it's okay. It's not bad. So here is AS, the best tour found. This is taboo search. This is similar aligning. So it does okay. It does great. However, now we want to look at a different algorithm that improves on this one here. So again, doesn't always converge to a single optimal solution. But let's still have a look at the new one. So these two folks, Dorigo and Gambardella, made some improvements. So they created a candidate list to restrict the choices of next cities. They used a different transition rule. They used a different pheromone trail update rule. and in particular, they have local updates of the Pheromone Trail. So now we're sort of like going to an area where we're getting inspired by nature rather than faithfully implementing it. So we'll just sort of take all the best stuff, really. So here's the idea of a candidate list. This is my image. So we have a city, and what we're going to do is we're going to look at its nearest neighbors, and we're going to look at a few of them. So we don't look at all of them. Okay, so this improves efficiency primarily. The transition rule is kind of really interesting. So here we grab an idea of simulated annealing, really, where, well, actually, no, it's exploration versus exploitation, something we have already heard about. So we have this tunable parameter Q0 to adjust the probability that an ant will explore exploration or exploit reinforce existing path. So if Q, we'll see that in a moment, is greater to Q0, then the transition rule is the same as we have seen before. But if Q is smaller or equal to Q0, it exploits the knowledge available about the problem. It just simply picks the shortest edge, the best edge among the ones that are still remaining. So here is the idea of simulated annealing. If we increase Q0 gradually, we would favor exploration early, and then eventually, because if it's very low, then this value here, as we will see, it's a random value, I believe, we will initially explore, and as it gets larger, we will eventually exploit. So it's an idea of simulated annealing. So let's run through this algorithm. So again, we put a small pheromone amount on each edge. We again place the ants on a randomly chosen city. We calculate the shortest tour found so far and its length. Okay, so again, we run this algorithm for a certain number of iterations, and for each ant we build a tour. So now let's have a look at the rules that we use to do this thing. So we have this candidate list, J, capital J, and it's for ant I. Sorry, it's for city I, for ant K. So what we're going to do is, over here we have this transition rule that I mentioned to you. If Q is less than Q0, we're going to use the same thing as we have seen before. Okay. Notice that we don't have an alpha anymore. We don't really need it. Since we have this if statement over here, we can just simply look at argmax. We don't have to normalize it. But if Q is greater than Q0, we'll simply pick something. We pick something amount J. Again, what we do over here is the probability of the city chosen is used by this rule over here. Okay. I'm sorry, I think I misspoke. The idea is that we use this one over here. This is what we have seen from the prior one, and over here, I'm sorry, we exploit. Over here we explore, over here we exploit. Okay, so if there isn't a city among the candidate list left, then we simply have to pick another one. We pick the closest one outside of the candidate list. All right, so here's something very interesting now. As the ant traverses the graph, there's sort of like almost like a penalty or an extra subtraction from the pheromone trail. So every time an ant goes down an edge, the pheromone trail decays. So if you want to sort of like make an analogy to nature, as they sort of trample on it, if you wish, it just decays a little bit. But the intent of this thing is a different one. And again, it goes back to the idea of exploration versus exploitation. So here's how we calculate the initial pheromone value, and we will also use it here in a moment. So the idea is, after a transition from I to J, we apply this pheromone update rule. So we do it right now. We don't wait until the ant is done. Again, we sort of like keep most of the pheromone value, but we decay it by a little bit. Okay, so we just sort of like remove a little bit. I'm sorry, the removing is done over here, and we just like add back that small amount. All right, so what we do then is, once all the ants are done, we do the typical, we calculate the length, for each ant and the tour if we have found and improved when we do this. So now, again, another thing that's kind of different over here. So before we updated pheromones based on every ant, but now we only do it for the optimal tour. So we put down pheromones for the current optimal tour only. Okay, so that's what we do over here. And then we copy the values into the next generation. So that's what we do over here. And again, these are tuning parameters that help us understand how much of the pheromones we put down. So notice that this is 1 over L plus 1, whereas before we have n times L and n over 1. 1 over this one. All right, so here again are some tuning parameters that we might use. Again, the local pheromone update rule, I already told you that if it's strong and a lot of ants go down this thing, then eventually will decay, and that will make it such that we explore different paths. So this one is actually very, very competitive. Again, as I mentioned, I apologize, only the ants with the best tour lay pheromones, and so encourages ants to search path near the best found so far. Here is a random solution to a problem. This is what we really want to look at, and so if we compare it to some other optimization algorithms, GA is genetic algorithms, EP is evolutionary programming, SA is simulated annealing. We're doing really well. So it's hard to see, I know, but this is bold-faced. So we have the best one over here. 535 is better than 542. And then over here on some different test set, I guess not as good as some of the other ones. These are different kind of test sets. All right, well, the idea here is that we have looked at intelligence throughout the course so far as something that uses symbols, that uses inference, that uses algorithms to come up with solutions. We looked at neural network architectures where we use lots of training data to develop classifiers. What we have over here is we have intelligence emerge from the interaction of many, many simple agents that we would not consider highly intelligent. And so a key aspect of this thing is pheromones. Without pheromones, this would not work. There would just be a bunch of random ants performing. All right, now, hopefully you found this interesting, or hopefully it raised your curiosity. I will talk to you later. Bye-bye.